So, welcome to this class in your course on mechanical operations. In the last 2 or 3 lectures, we have been covering one mechanical operation, which is synthesis of nanoparticles, particularly the top down method. But starting today, we will deal with some more examples of mechanical operations that are perhaps a little more conventional. The first mechanical operation that we will talk about is separation. Separation is something that is a requirement in many process industries. You are typically trying to separate product from byproducts, or product from impurities, or product from feed, or multiple products from each other. All of these require that you have to have a way of separating them. Now, separations can be done by mechanical means, or they can be done by other means as well, which could be chemical or even diffusional. The class of separations we are going to talk about first is mechanical separations. Mechanical separations are typically applicable to particles that are at least 0.1 microns or larger. If what you are trying to separate has a size that is less than 0.1 microns, the mechanical separation methods that we are going to talk about will not work, and in fact diffusional methods can then be used, because as we have discussed before, as particle sizes decrease, diffusion kicks in as a predominant mechanism. There are 3 types of mechanical separations that we are going to deal with first. In general, a mechanical separation by definition is one that depends on certain mechanical or physical properties of the materials involved. Things like size, shape, density would be examples of such properties. So, the 3 methods that we are going to talk about first: screening / sieving, filtration and sedimentation, are methods that are considered to be mechanical separation methods because they use one or more of these properties to effect the separation. In particular, the first method that we will talk about only involves shape and size, and that is screening or sieving. I am sure you are all familiar with screens and how they work, and sieves, but as you can imagine, in any screen or what you have is a set of meshes or holes or apertures through which particles pass. Now, it is a very simple method of separation. The feed will approach the screen, and depending on the relative size of the particles that are approaching the screen and the mesh size of the screen itself, the particle will either pass through or get collected at that screen. So, there is basically a cutoff size. Any particle that is below the size of the aperture will pass through to the next stage. Any particle that is larger than the size of the aperture will get retained. But that is a very simplistic view, right? That is assuming what? Spherical particles for one thing. But in reality, you may have particles that are highly non-uniform in their shape distribution, in which case your angle of approach will actually have a huge impact on the retention efficiency, particularly as the particles get to be more elongated or the aspect ratio starts to depart more and more from a value of unity. You will see that the angle of approach starts to have a significant effect on the collection efficiency. It is only in the case of a perfectly spherical particle approaching a hole that you can have a very clean cutoff size, where everything below that size passes through and everything above that size gets retained. When that happens, it is called an ideal screen. So, there is an underflow and there is an overflow. All the undersized particles go with the underflow, and all the oversized particles go with the overflow. If this happens perfectly, the screen effectiveness is considered to be 1 and the screening error is considered to be 0. We will look at how these parameters are defined. Now, how do you actually feed the particles? There are many ways in which you can feed, but a simple way is just gravity. Particularly in industry scale screens, some of which you may have seen either during your any visits to industry or in pictures and so on, grizzlies or large scale industrial screens where the material essentially drops onto a screen and it is basically gravity fed. But you can also imagine feeding mechanisms that involve applied force. For example, if you want to make sure that something gets screened effectively, you may actually apply pressure against the screen. So, instead of just dropping the material onto the screen, you can take a brush and actually brush it against the screen, so that anything that is undersized you make sure will go through. You can even use centrifugal force and other means to increase the velocity at which the particles approach the screen, because that is one of the factors that contributes to how effective the screen is. In fact, if you imagine how a screen works, what are some possible problems or drawbacks that can happen? It goes back to some of the things we have studied earlier in the course. Cohesion. If your feed is such that the particles are agglomerating with each other, clearly that is going to impact their screening efficiency. Or adhesion. If instead of passing through the apertures, the particles stick to the sides of the wire, again, or to the sides of the feeding mechanism, whatever it is, whether it is gravity fed or other ways, again screening is not going to be perfect. There is something called a near mesh size. When the approaching particle size is almost the same as the aperture size, that is when screening actually becomes very tricky, because whether the particle gets into the underflow or the overflow can depend on very subtle factors, and therefore it is very hard to predict the screening behavior, when particularly for particles that are approximately the same size as the mesh size. By the way, mesh size or mesh number is something that is defined differently in different standards. In fact, in most of the international standards, the so called mesh number is related to the number of apertures per unit length. For example, a mesh size of 200 may refer to 200 apertures per centimeter of the screen of the wire length. So, in other words, the higher the mesh number, the finer the mesh, and that is in fact how most of the international standards are written. But the Indian standard for mesh size actually is a lot more logical. It basically, you can take the mesh size or mesh number that is defined and multiply it by 10, and that gives you the size of the particle that will pass through in microns. In other words, in the Indian mesh number definition, a mesh number of 10 says that the aperture size is 100 microns. So, any particle that is larger than 100 microns will be retained, and any particle that is smaller than 100 microns will be passed through. So, in the Indian classification, the smaller the number, the finer the screen. Okay? So, that is a subtle difference you have to kind of keep in mind. In fact, there are lots of textbooks, reference books that have tables of mesh sizes, both in the Indian classification scheme as well as the ASTM and the British classification and so on, and what they actually correspond to in terms of sizes, and that is something you should read up and get familiar with. Not necessarily something you need to memorize. These tables are available to you. You can easily access them on the internet or in any textbook and so on, but it is important for you to understand the different mesh classification methods that are used by different standards. When you talk about screening, there are really two important parameters that you have to be aware of. One is screening effectiveness and the second is screening capacity, and frequently the two are in conflict with each other. If you try to increase the effectiveness of the screen, much of the time you will end up reducing its capacity. How do you define screening effectiveness? If you look at the way a screen works, suppose you have particle size on this axis, there is something called DPC, which is the critical particle size, or it's a size that separates the underflow from the overflow. the implication is any particle that has a size that is smaller than dpc will be passing through, and any particle whose size is larger than dpc will be retained. So, if you plot this in an ideal screen, you may have two separate curves that represent in let us say that size is increasing this way. This is underflow and this is overflow, and these are the size distributions in the two. By the way, a single screen will only give you a separation between two sizes, right. It will only separate particles smaller than a certain size from particles that are larger than a certain size. However, in most applications, whether in the laboratory, you will be working with a sieve setup, for example, in the mechanical operations lab, or in industry where you will be working with a set of screens, you typically do not do a single size separation. You have a series of screens that are sequential, and the screen size or the sieve size will keep decreasing. So, the coarsest screens will be on top and the finest screens will be at the bottom. So, the way this works is you feed from the top, and at each of the screens you separate particles that are larger than that size, the smaller ones go through, and again, so that keeps happening. So, by using a set of screens you can actually get a distribution of particle sizes. And in fact, we have looked at methods of analyzing particle size distributions before. You can look at particles that are retained in a particular screen and obtain its particle size. You can represent it in tabular form, in differential form, in cumulative form. So, all of those things that we did with particle size distributions earlier can be applied in this case also. So, the finest particles will pass right through the smallest screen and typically get collected on a pan where they will be weighed. So, in a standard sieve setup or screen setup, the fines that pass through the smallest screen are typically not subjected to subsequent size analysis, but rather gravimetric analysis. However, size analysis will be done for all the other fractions just based on where they are retained. So, in a clean or an ideal screen, there will be no overlap. The largest size in the underflow will be just smaller than the smallest size in the overflow. However, what is going to happen in reality? Are you going to be able to control it this well? No, because some of the problems I was talking about earlier. If you have non-spherical particles, there is a mechanism called blinding where so much material accumulates in one place that no more particles can pass through. So, periodically the screens have to be cleaned and so on. Angle of approach, if you do not have particles approaching the apertures at a normal angle, there is always a potential that they will get trapped even though they may be smaller than the actual size of the aperture. So, there are many things that can cause an overlap between these two fractions. So, the amount of undersized material in the overflow and the amount of oversized material in the underflow are called the errors in your screen. And the whole point of a screening apparatus is to try and minimize these errors. So, you want this overlap to be as small as possible for a clean separation. But understanding that there is always going to be this overlap and your screening effectiveness is never going to be 1, there are formulae that have been developed to quantify screen effectiveness. So, one easy way to do that is just through mass balance. If you say that F is your feed amount and let us say that O is the material that comes out in your overflow and some U is your material that comes out in your underflow. And let us take a simple case of just two components that you are trying to separate, A and B. Let us say that XAF is your mass fraction of A in feed and XAO is the mass fraction in the overflow, and XAU is your mass fraction in the underflow. And let's say that A is your undersized material, okay. And there is a component B which is your oversized material, and 1 minus each of these will give you the corresponding mass fractions of B in the feed stream, overflow and underflow. So, how do you do the mass balance in this case? Obviously, if you look at total mass, F equals O plus U. If you do component A mass balance, XAF times F will be equal to XAO times O plus XAU times U, right. So, here what you can do is substitute one of these. Let us say that you call this O as F minus U, by applying the previous total mass balance. So, you can write it this way, and now you can bring terms corresponding to F to one side. So, it will be XAF minus XAO times F equals XA or equals U times XAU minus XAO, right. So, you can write U by F as being equal to XAF minus XAO divided by XAU minus XAO, and of course, you can write O by F as 1 minus this, and you will get an expression for that. So, keep that for the time being. Now, how do you define screening effectiveness? The effectiveness can be split into two parts. You can look at an effectiveness with respect to the underflow and an effectiveness with respect to the overflow, and the multiplication of the two will give you the overall effectiveness, just like probability, right. So, if you look at the effectiveness, or screening effectiveness, so let us first take the underflow. Let us call that EU. How would you define that? Any suggestions, ideas? I mentioned that A is undersize, B is oversize, right. So, if you want to look at the screening effectiveness with respect to the underflow, what should it be? All of A should be in the underflow, right. So, if you look at U, which is the total underflow quantity, times XAU, and you divide it by F times XAF, that should give you the effectiveness with respect to the underflow. And here you can substitute for U by F from that expression, okay. Not going to do that for you, it will just make it a very, very long expression, but you can do that. And similarly, E for the overflow, you can write as O times 1 minus XAO times F times 1 minus XAF, since that will measure the effectiveness of the screen in containing all of B material in the overflow, right. So, again from this expression you can substitute for O by F, and finally the overall screening effectiveness E equals EU times EO. Okay. So, just go through this exercise. So, basically once you write this, you will be able to express this overall screen effectiveness just in terms of the mass fractions of A and B in the underflow and overflow streams, which you can easily measure. Ideally E should be equal to 1, but you will see that when you actually do the calculation, depending on how the split happens, you may get a value that is close to 1 or not. So, that is screen effectiveness. So, this is one of the problems you will work out in the tutorial. You will be given certain numbers, you have to be able to calculate screen effectiveness based on the measurements on the feed, the underflow and the overflow. Now, what is screen capacity? I mentioned that those are the two important parameters with respect to screening. Screen capacity is a measure of how much quantity of feed the screen can handle per unit time per unit area. Obviously, the higher the capacity, the more material it can process. But what is going to happen if you keep increasing your feed amount? Some of these problems that we talked about earlier, agglomeration will become worse. Interference of one particle approaching the screen by the next particle can become worse. Blinding can happen. Eventually, you may even start to have damage of the screen. If you have particles that are approaching at some velocity and you have a large number of them impacting in a certain location, you can actually start to create small holes and other pathways that particles can escape through. So, capacity is something that you want to maximize, but at the same time you do not want to affect your screen effectiveness. So, it is a classical optimization problem. I do not think you have taken a course in optimization yet, but one of the skills that chemical engineers learn is when you have when you are trying to optimize something, but subject to a constraint, how do you do it? Here you are trying to maximize your screen effectiveness, but subject to a capacity constraint. I mean, clearly if you just take small amounts of material and feed them very slowly and very carefully, you can get 100% screen effectiveness, but that is not going to work for you in a production environment, right. Similarly, you can just pump tons of material through and you will be happy with the throughput, but then your screen effectiveness is going to drop down pretty badly. So, it is a constrained optimization problem, and there are actually algorithms and computer programs that have been written for standard screens to enable you to do that. But one of the things that you need to look at is what does screen effectiveness really depend on. I mean, this is a mathematical representation based on data, but if you are a designer and you are trying to design a screen, how would you try to maximize effectiveness? What dictates the success of a screen? Actually, it is two parameters. One is the number of times a particle impacts a screen, and the second is the screening success based on each impact. So, for example, when you are trying to screen a particle mixture and you feed it through, the first time there is a chance that a particle that is supposed to penetrate may not, because of the various reasons I talked about. But if I have a way of sort of recycling it, so instead of processing it just once, if I can process it say 5 times, the probability is eventually that particle will approach the screen at the right angle in the right condition, and it will pass through because theoretically it is supposed to, right. So, the number of impacts of a particle on a screen surface has an effect, almost a direct correlation on its screening effectiveness. And similarly, for each impact, what is the probability that it will get screened? Now, there are two types of screens. There are static screens where you have a screen that is held in place and you are just putting material on top of it and hoping that things will happen as per theory, undersized particles will go through, oversized particles will be retained. However, things do not always happen that way. So, you need to help the process along. So, some of the techniques that have been developed is instead of a stationary screen, you can have a screen that is vibrating, right. What does the vibrating screen do for you? It shakes loose any particles that get stuck on the screen surface. It can de-agglomerate particles that come in an agglomerated state, and in fact a high frequency vibration with small amplitude is ideal for defeating some of these intrusive mechanisms that happen on the surface. So, a vibrating screen is very commonly employed. When you go to the lab in mechanical operations and do the sieve experiment, you will see that essentially what we use is a shake arrangement. It is called a sieve shaker. So, you mount a set of sieves and they are held in place, and the whole setup is shaken in an eccentric manner at a certain RPM, and this shaking process again can help dislodge particles that might get stuck on the screen surface. You can even use stronger forces. As I said, taking an abrasive and actually rubbing particles on top of the screen can be done in a small scale in a laboratory, but it is even done in large scale screens in industry, where you are physically pushing the particles against the screen surface. So, all of these are methods by which you try to increase the probability of screening for a single particle, right. And then when you combine it with a strategy to provide multiple impacts per particle, you can start increasing the capacity and the screening effectiveness simultaneously. The screens that you see in lab or in industry, I mean, have these square apertures, right. I mean, they have a configuration that's basically looks like this, and as I said, typically these are square in shape, and this is the size, the aperture size or the mesh size that dictates which particles go through and which particles do not. Clearly, the how thick the wire is has a bearing also on screening effectiveness. You want the mesh material to be as thin as possible, but at the same time you do not want it to be damaged. So, that automatically limits the type of material that you can make these screens out of. The meshes have to be made of metal. You cannot have screens that have plastic meshes, they just will not last, especially when you are trying to do repeated uses in industry. You really need metal meshes, and it is also important that the size of the metal of the wire must be kept, as I said, as thin as possible, but it also must be very uniform, because you are assuming that this is a mesh number 10 screen, you are assuming that every aperture is 100 microns in size, and if you have non-uniformity in that can again severely impact your underflow contamination of overflow and overflow contamination of underflow and so on. Another parameter that affects screening effectiveness is just humidity. Moisture plays a role in determining screening effectiveness when you are doing dry screening, because moisture promotes particle to particle adhesion, it promotes cohesion, it also can sometimes result in oxidation of the metal, which can actually increase its size, especially when you start talking about screening down to about 20 microns. By the way, the smallest size that you can screen effectively is about 40 microns. Now, there are micro sieves that have been developed more recently that have extended the lower limit to about 20 microns, but you really cannot go below 20 microns as far as mechanical screening or sieving is concerned. If you are trying to separate particles that are smaller than 20 microns, then you are better off using other techniques we will talk about, such as filtration. Sedimentation is another technique that is primarily useful for the larger particles, because the finer particles will just float to the top, they really will not get separated. So, of the mechanical separation techniques that we will talk about, only filtration is capable of separating particles that are finer than about 20 microns. So, as the mesh size gets smaller, it becomes, things like moisture can start to have significant effect. However, there are also what are known as wet screens. So, instead of screening or feeding the material in a dry state, you can actually prepare a suspension and feed the suspension to the screen. Now, what would be the advantages and disadvantages of a dry screen versus a wet screen? The biggest advantage of a wet screen is that because the particles are suspended in moisture, the tendency to cohere will be much less. All those forces of attraction that we have talked about, many of them will be significantly reduced when you are suspending the particles in water, for example. So, it is very possible to feed particles to a screen in an unagglomerated state when you use wet screening. Also, the relative velocities at which the particles can approach the screen can be enhanced by using a liquid as a medium compared to air or some gas. But what would be the disadvantage of using a liquid medium to do screening? The liquid medium itself can, because it has viscosity and because it has surface tension, it can act as a buffer essentially and provide like a shielding layer that makes it difficult for the particle to approach a hole and go through it. Because as you can imagine, if you have a particle that is approaching this aperture, and let us say that it has a film of moisture around it, the moisture is actually going to influence the way that it passes through the aperture, right. So, you can actually have capillary effects that provide a liquid bridge between the particle and the aperture through which it's trying to make its way through. And so, there are some issues also with wet screens compared to the dry screens. But if you are operating a dry screen, it is very important to do it in a humidity controlled environment. That is a key point. A soft particle, by the way, is also more difficult to screen compared to a hard particle, because again in a screen you are just relying on physical motion, size and shape. So, what happens if you have a particle that's hygroscopic, that has, let us say, absorbed water or swells when it comes in contact with water? Its size actually changes, right, with humidity. And so, particularly when you are dealing with particulate materials that can absorb water, you have to be very careful that you do it in an extremely dry environment. The other challenge in screens is that once you have collected the particles on a screen, how do you do analysis of the material that has collected? So, typically you have to remove the materials from the screen into some kind of a sampling device. It is easy to do gravimetric weighing. You can just weigh the screen before and after, and it will tell you total amount of material that has collected. But if you want to do subsequent analysis, you have to be able to recover the particles that are retained by the screen, and also you have to clean the screen to be able to reuse it, right. So, you have to make sure that any particle, any material that is retained on a screen can be completely removed from the screen as well. And that again is difficult when you have moisture present, because instead of having loose particles on the screen which can be easily brushed off, you will have particles that are kind of stuck to the screen, and this can build up over time. The first few times it may not be a significant factor, but as you keep reusing the screen, you will find that the screening effectiveness keeps decreasing, not because of any changes in your feed, but because of changes in your screen itself, and in terms of how clean it is, how uniform the pores are or the holes are, and also how close the particles are able to approach the screen. The whole point in screening is until the particle actually encounters the screen, it should be unaware of the screen. That is kind of the ideal situation. So, it approaches the screen, it has a certain size, it sees an opening that's larger, it passes through, right. That is the way it is supposed to work. But if you actually start depositing some material on the screen, or you start having some deterioration of the screen because of processing conditions and so on, that is not going to happen. The screen itself, the changes in the topography of the screen can start having an effect on how particles get passed through. So, that again can impact your screening effectiveness. So, what we have discussed so far are just the screens and the sieves that are typically used in laboratory or in industry to separate materials by size and shape only. But as I said earlier, there are situations where you need to be able to separate particles based on not just size and shape, but other physical properties as well. And the two most common methods of separation after screens and sieves are filtration and sedimentation. So, in the next class we will talk about filtration in some detail, probably the next 2 classes, and then we will talk about sedimentation in the next class, and after that we will start talking about again production or synthesis of particles primarily by ball milling and other means of size reduction, because next to separation the most common mechanical operation in industry is size reduction. So, that is another mechanical operation that we need to be quite thorough with. All right. So, any questions on what we have talked about today? All right. So, I will see you in the next class.